feeling like you're constantly playing catch-up with information. Like you need to understand something deeply, but you're short on time and maybe just overwhelmed by all the stuff out there.
Yeah, that's exactly why we started the deep dive. We tried to sift through the research, the lectures, all those, information mountains to bring you the core insights. Think of it as, well, your express route to being truly informed.
Designed for you, the listener.
Exactly. With a few surprising discoveries along the way, hopefully.
And today we're tackling a topic that's, well, it's becoming indispensable for anyone in creative fields, really.
Yeah.
The foundational concepts of artificial intelligence for designers.
Right. We're drawing from this really insightful recorded lecture to unpack these ideas.
Yeah, in a way that's not just educational, but, genuinely fascinating and hopefully immediately applicable to your work.
So our central goal here in this deep dive is to get a handle on how AI, and specifically its workhorse, machine learning, actually operates.
But from a designer's viewpoint.
Exactly. We want to sort of take away the mystery, reveal the underlying logic.
And I'm really excited about this. We're going to demystify the surprisingly straightforward heart of machine learning using a really powerful analogy.
Yeah, it's a good one.
By the end, you should have a fresh perspective on how AI actually learns. Okay, so let's jump in. AI and machine learning.
Yeah.
What's the crucial distinction a designer needs to grasp first?
Well, the key thing is, machine learning isn't really a type of AI.
Right.
It's more a method, a set of techniques that lets us achieve artificial intelligence. The focus is squarely on computers learning from data, identifying patterns.
Right, letting the data guide the process.
It's fundamentally data-driven learning.
Data-driven. Okay, I can definitely see how that applies in design.
Yeah.
With user feedback, analytics, all that stuff. So how does the data actually lead to learning? What's the core engine?
Okay, think of machine learning at its most basic level as dot and line drawing.
Dot and line drawing?
Yeah. Imagine a blank canvas. Each piece of data you have, maybe a user interaction, a design preference, it's a dot on that canvas.
Okay.
And these dots are scattered across the canvas based on their characteristics, their features.
Right, I'm picturing that. A canvas full of data dots. So where does the line come in?
Ah, the line. The line represents a function. Think of it as a kind of underlying rule or relationship that best explains the arrangement of those dots.
Okay.
And the whole goal of machine learning is to find that line, whether it's a straight one or maybe a more complex curve that fits the pattern of your data most accurately.
So it's about finding the best visual explanation kind of for how the data behaves. How does the machine actually figure out where to draw that line?
Well, it does this by iteratively adjusting internal weights.
Weights?
Yeah, think of weights as the knobs the machine can turn to fine-tune the line's position and angle.
Okay, adjustable knobs.
And to know if it's turning them in the right direction, it uses something called a loss function.
Loss function.
Right. The loss function basically measures how far off the current line is from all the dots. It calculates the error.
Okay.
The machine's aim is just to keep adjusting those weights, turning those knobs, until the loss is as small as possible, which means the line is the best possible fit for the data it's seen.
Weights is adjustable knobs. Loss function measures the error. That makes the abstract stuff a lot more tangible, yeah. Now, you mentioned data is crucial. What makes certain data really, good for this learning process?
Well, the lecture really hammered this home. We need data that actually contains patterns that can be learned.
Right.
And a key insight was this. If you, as a human designer, look at the data and you just can't see any consistent trends or relationships, then an AI model isn't going to magically find them either. It's like trying to see a picture in just random static.
Right. If we can't spot the signal in the noise, we can't expect the AI to.
Yeah.
So what are some red flags? What kind of data hinders learning?
Well, think about noise first off. Just irrelevant or misleading information mixed in with the real data points that can obviously confuse the model.
Okay.
Similarly, if your data is very sparse, meaning you have very few dots compared to how complex the pattern you're trying to find is, it's really hard to establish a reliable line.
Not enough evidence, basically.
Exactly. For effective learning, those underlying relationships need to be present and, well, reasonably clear in the data itself.
Okay, so we're aiming for clean, representative data. But let's be real, data is often messy. That's where data preprocessing comes in, right? The lecture this is like a MOST.
Oh, absolutely. Non-negotiable, really. Data preprocessing is this whole set of crucial techniques to get your data ready for learning and ensures you get meaningful results.
So what does that involve?
Well, one important technique is noise removal, filtering out that irrelevant stuff we just talked about.
Like fixing typos and feedback.
Exactly, or maybe smoothing out jumpy sensor readings, things like that.
Makes sense. Clean up your materials before you start building. What else?
Scaling is another big one. This is really important when your different data features have vastly different ranges.
How so? Give me an example.
Okay, imagine you're analyzing website user behavior. You might have the number of clicks, which could range from, say, 1 to 100. But then you also have time spent on page, which might range from a few seconds to, I don't know, several minutes, maybe even hours.
Right, very different scales.
Very different. If you feed that raw data into a model, the features with the bigger numbers, like time and seconds, could just totally dominate the learning process, even if they aren't more important.
Oh, yeah.
So scaling brings all the features onto a comparable numerical range.
It's the playing field, basically.
Yeah.
Make sure one type of data doesn't overwhelm the others just because its numbers are bigger.
Precisely. Normalization is similar, but it often involves squeezing the data into a very specific range, maybe like 0 to 1 or -1 to +1, certain algorithms like that. Then you've got the really crucial task of handling outliers.
Outliers, those weird data points that don't fit.
Yeah, those extreme values way off from the general pattern, like that user who spends 10 hours on one page, maybe.
Right.
They can really skew the learning process, pull that line way off course, so you might need to remove them or maybe transform them somehow.
Okay, deal with the extremes.
Finally, there's dealing with missing values. Super common in real-world data. You just have gaps. The lecture mentioned various ways to handle this: imputation methods.
Imputation?
Yeah, strategies for filling in those gaps. You could use the average value of that feature, or use more complex statistical methods like regression-based imputation, or even just remove the data points that have missing info.
So different ways to fill the blanks.
Right. And sometimes you might even test different approaches to see what works best for your specific data and the problem you're trying to solve. It often involves a bit of experimentation.
Wow, okay. It really sounds like a huge chunk of the work is just getting the data into shape before the AI even sees it.
It often is. Garbage in, garbage out, as they say.
Right. Now, the lecture also mentioned different kinds of machine learning problems. Regression and classification. Can you give us the designer's definition? Let's stick with the dots and lines.
Okay, dots and lines. Regression problems are basically about drawing a line and predicting a value along it.
Along it, okay.
The goal is to predict a continuous output, a number somewhere on a scale. Think predicting, maybe, how much a user will like a new design feature on a scale of 1 to 10 based on their past behavior.
Okay.
You're drawing a line that best fits the relationship between past behavior and ratings, and then you use that line to predict a future rating value.
A continuous prediction. Got it. What about classification?
Classification problems are more about drawing a line and dividing the dots into categories.
Dividing.
Yeah. Here, the goal is to assign data points to specific groups or classes. A design example. Maybe predicting whether a user will click a call to action button, yes or no, based on design elements and user traits.
Okay.
You're essentially drawing a boundary, a line, that separates the will click dots from the will not click dots.
So discrete predictions, putting things into separate buckets. Positive, negative, click, no click.
Definitely.
It was interesting. The lecturer mentioned the same data could sometimes be tackled either way. How would that work in design?
Yeah, that's a good point. Imagine you're analyzing user feedback on a new website layout.
Okay.
You could frame it as a classification problem. Is the feedback positive or negative? 2 buckets.
Right.
Or you could treat it as a regression problem by trying to predict, say, a sentiment score on a continuous scale, maybe from -1, very negative, to +1, very positive.
Okay.
The choice really depends on the level of detail you need in your prediction and how you plan to use that information to actually inform your design decisions.
That makes total sense. The way you frame the question shapes the AI's whole approach. Okay, moving on. Something that sounds a bit scary. The curse of dimensionality. What's the challenge here for designers working with lots of data?
Right. The curse of dimensionality. It sounds dramatic, but it's a real thing. It basically describes the problems that pop up when your data has a very large number of features or dimensions.
Too many features. I thought more data was good.
Well, more data points can be good, but having too many features per point can actually make it harder for machine learning models to find meaningful patterns.
Outcome.
Imagine trying to find a specific shade of blue in a paint store. If they only have a few swatches, it's easy.
Right.
If they have thousands of slightly different blues, It gets much harder to pinpoint the exact one or even see clear groups.
Okay.
With high-dimensional data, the data points become very spread out, almost equidistant from each other in that high-dimensional space. The relationships and patterns can get diluted. It just gets noisy and hard for the model to learn effectively.
So just piling on every possible piece of information about users isn't always the best strategy.
Not necessarily, no. It can backfire, and that's where dimensionality reduction techniques come in.
Oh, okay. Ways to simplify things.
Exactly. Methods to reduce the number of features in your data, but while trying to keep the most important information. The lecture mentioned two main types, linear and nonlinear.
Let's start linear. PCA was mentioned, principal component analysis. How should a designer think about that?
Okay, PCA. Think of it as finding the most important underlying themes or factors in your data.
Themes.
Yeah. So if you have tons of user feedback comments on a website, PCA might help you identify the core aspects users are reacting to most strongly, maybe navigation, visual appeal, loading speed, even if they use different words.
Ah,
It
yeah.
essentially tries to find a smaller set of new artificial features, the principal components that capture the most variance, the most information from your original data. It lets you work with fewer, more meaningful dimensions.
Boiling it down to the essentials. Got it. What about the nonlinear one, TSNE?
TSNE, that stands for T-distributed stochastic neighbor embedding. Bit of a mouthful.
Yeah.
It's more about visualizing high-dimensional data in a lower-dimensional space, like a 2D scatter plot.
For visualization.
Primarily, yeah. It does it in a way that tries to preserve the local relationships between data points. So points that are close together in the high-dimensional space should end up close together on the 2D map.
Okay.
Imagine you have data about different design styles, maybe defined by dozens of attributes. TSNE can help create a visual map where similar design styles cluster together.
So you can actually see the groupings.
Exactly. The lecture used that classic example of visualizing handwritten digits. Each digit image is made of many pixels, right? High dimensions. But TSNE can plot them so all the O's are grouped together, all the ones are grouped together, and so on a 2D chart. It helps you see structure.
Okay, so PCA helps find core factors, TSNE helps visualize clusters. Both handle that dimensionality curse. Now, let's get into neural networks and deep learning. The lecture presented these as solutions for nonlinear problems. What makes them so powerful for complex design data?
Right. So many traditional machine learning models, they kind of assume linear relationships or simpler patterns. They can struggle when the reality in the data is much more complex, more wiggly. Nonlinear.
Exactly. Neural networks, especially deep neural networks, the ones with multiple hidden layers, are specifically designed to learn and model these really intricate nonlinear patterns that you often find in real-world data, including design data.
Can you paint a simple picture of a neural network structure for a designer? How does it work?
Sure. Think of it like a series of layers. You've got an input layer where you feed in your data, maybe design parameters, user characteristics, pixel values from an image.
Okay, start.
Then at the other end, you have an output layer that produces the result. Maybe a prediction like user will click, or perhaps even a generated design element.
Input and output. What's in between?
In between, you have one or more hidden layers. Each layer is made up of interconnected neurons or nodes.
Neurons.
Yeah, sort of like simplified brain cells. And each connection between neurons has a weight associated with it. This weight represents the strength or importance of that connection.
Weights again, like the knobs we talked about earlier. Exactly the same idea. These weights are the parameters the network tunes as it learns. It's like adjusting how much influence one neuron has on the next.
Okay. And what happens inside a neuron?
Well, inside each neuron, there's usually an activation function.
Activation function.
Think of it as a simple decision rule or a filter. It takes the combined input signals coming into the neuron, processes them, and then decides whether the neuron should fire, pass a signal onto the next layer, and how strong that signal should be.
So it decides if the info is important enough to pass along.
Pretty much. The lecture mentioned a few common ones like sigmoid, ReLU, leaky, ReLU. They're just different mathematical functions that act as these filters, each with slightly different properties.
And the learning happens by adjusting those weights.
Yes. It's typically done through a two-step process. First, you feed data forward through the network from input to output to get a prediction. Then you compare the prediction to the actual target, calculate the error using the loss function.
The loss function again.
And then you propagate that error signal backward through the network. This backpropagation step tells the network how to adjust each weight slightly to reduce the error next time.
Forward flow, calculate error, backward adjustment. It sounds like a continuous refinement loop.
It is very much like iterative design, actually. You
Yeah.
keep feeding it data, and it keeps tweaking its internal weights to get better and better at the task.
Okay. Now, how does the network really know if it's getting better? Let's
Yeah.
revisit that loss function. How can a designer think about this concept? It seems critical.
It is critical. Imagine you're evaluating different versions of a design against some key metrics, say user engagement or conversion rate. The loss function is like that metric for the AI.
A score of how well it's doing.
Exactly. It's a quantitative measure of how wrong the AI's current output is compared to the desired target outcome.
Okay.
For regression problems predicting a number, the loss might be the average squared difference between the predicted numbers and the actual numbers. For classification, putting things in categories, it might measure how often the AI picks the wrong category.
And the lecture mentioned specific types, R squared.
Yeah, R squared is common for regression. A score of 1.0 means a perfect fit, closer to 1 is better. For classification, something called cross-entropy is often used, where a lower score indicates better performance. The specific function depends on the problem.
So the whole learning process is basically trying to minimize that loss score, get the wrongness as low as possible.
Precisely. The learning algorithm tries to tweak the network's weights in a way that makes the loss function value go down,
How does it know which way to tweak?
often using an optimization technique like gradient descent. Think of the loss function as defining a landscape with hills and valleys. Gradient descent is like rolling a ball down the hill. It takes small steps in the steepest downward direction to find the bottom of the valley, which represents the minimum loss.
Rolling downhill to find the best solution.
Yeah.
Nice analogy. Now, the lecture also brought up underfitting and overfitting. These sound important for knowing if the learning is actually working well.
Hugely important. These are common pitfalls.
Can you explain them again, maybe with a design analogy?
Sure. Underfitting is like creating a design that's way too simple. It just doesn't capture the nuances of the user needs or the problem. It performs poorly on the data you trained it on, and it performs poorly on new data, too. It just hasn't learned the pattern.
Too basic. Okay, what about overfitting?
Overfitting is the opposite problem. It's like designing something that's so perfectly tailored to the very specific feedback from your initial small group of testers that it completely fails when you show it to a wider audience. It learned the training data too well, including all its quirks and noise, but it didn't learn the underlying generalizable principles.
So it memorized the examples instead of learning the concept.
Exactly. It performs brilliantly on the training data it already saw, but its performance tanks when it encounters new, unseen data.
And how do we detect if our AI model is overfitting, like our overly specific design?
This is where validation data comes in. It's standard practice. You don't train the model on all your data. You hold back a portion, the validation set. You train the model on the training set, but you regularly check its performance on the validation set, which it hasn't seen during training.
Okay, like testing on a fresh audience.
Precisely. If you see the model's performance on the training data continuing to improve, but its performance on the validation data starts to get worse, that's the classic sign of overfitting. The model is starting to memorize the training noise instead of learning the general pattern. That tells you need to stop training or maybe simplify the model or get more data.
So the validation set is our reality check.
Okay, super important. We've talked a lot about learning from existing data sets. What about reinforcement learning? The lecture mentioned it needs an environment. How is this different?
Yeah, reinforcement learning, or RL, is a different beast altogether. Instead of being trained on a pre-existing labeled data set, an agent, that's the AI algorithm, learns by interacting directly with an environment. It takes actions within that environment.
And based on those actions, it receives feedback in the form of rewards or penalties.
Rewards and penalties, like getting points in a game.
Exactly like that. The lecture used the Mario game example. The AI agent is Mario. The environment is the game level.
Right.
The agent tries different actions, move left, jump, etc. It gets a reward for good outcomes like collecting coins or reaching the flag. It gets a penalty for bad outcomes like falling into a pit.
And it learns from that feedback.
Yes.
Yeah.
Over many, many trials, it learns a policy, a strategy of which actions to take in which situations in order to maximize its total cumulative reward. It learns through trial and error, basically.
Trial and error based on environmental feedback. How could this apply to design problems?
Well, imagine an AI trying to optimize the layout of elements on a web page to maximize user engagement.
Okay.
The environment is the web page simulator, or maybe even the live site. The agent is the AI trying different layouts, moving buttons, changing text sizes.
And the reward?
The reward could be an increase in click-through rate or time spent on page, maybe conversion rate. The penalty would be a decrease. Through lots of experimentation, the AI could potentially discover a highly effective layout.
Interesting.
The lecture also mentioned potential applications in things like robotic object manipulation, or even optimizing the physical layout of a room or a building based on defined goals like workflow efficiency and penalties for clashes or inefficiencies.
So it's good for problems where an agent can act and get feedback.
Exactly. The key things you need are that defined environment, a set of possible actions for the agent, and a clear reward penalty system linked to the goals.
That's a really different way to think about AI learning. Okay, let's circle back to the data itself. The lecture really emphasized understanding the different types of data we might encounter. Why is this so critical for a designer wanting to use AI?
Because knowing your data is absolutely foundational. The type of data you have fundamentally shapes what you can do with it and which AI techniques are appropriate.
Okay, so what were the main categories?
Well, the lecture broke it down a few ways. You've got things like sound, often represented as 1D sequences of numbers.
Right.
Then there's structured data. This is the neat, organized stuff like spreadsheets, CSV files, databases, JSON files. Think user demographics in a table or product sales figures. Rows and columns.
The tidy data.
Pretty much. And then there's unstructured data. This is everything else, text from user reviews, social media posts, audio recordings, images, videos, stuff that doesn't fit neatly into rows and columns.
And the type of data points us towards certain AI tools.
Very much so. The lecture highlighted that deep learning models, and especially things like large language models, LLMs, are particularly powerful for handling unstructured data.
Why is that?
Because they can often automatically learn the relevant features directly from the raw data, like learning patterns in text or pixels, without needing you to manually define them first.
Oh.
Whereas traditional machine learning methods often work really well with structured data, where the features, the columns in your spreadsheet are already clearly defined and meaningful.
Makes sense. The lecture also broke data down further. Continuous, discrete, ordinal, nominal. Quick designer examples for those.
Sure. Continuous data is anything that can take any value within a range, usually measurements, like the exact time a user spent on your site or the precise screen width in pixels.
Okay. Discrete.
Discrete data can only take specific separate values, usually counts, like the number of times a user clicked a button. You can't click 2.5 times.
Ordinal.
Ordinal data has a meaningful order, but the intervals between the values aren't necessarily equal. Think user satisfaction ratings. Very dissatisfied. Neutral. Very satisfied. There's an order, but the distance between them isn't mathematically precise.
Like small, medium, large.
Exactly. And finally, nominal data is categorical data without any inherent order, like the type of device a user is on, mobile, desktop, tablet, or maybe different user personas. They're just distinct categories. And understanding these distinctions is crucial because it helps you choose the right analytical methods and the right machine learning models. You wouldn't use a regression model designed for continuous data to predict a nominal category like device type, for example.
Right. Matching the tool to the data type. Now, the lecture made a really strong point, maybe even a surprising one for some. Understanding the design problem and having domain knowledge is actually more critical than just knowing the AI techniques themselves. Why is that perspective so important?
It's absolutely crucial, especially for designers. You can have access to the fanciest AI tools in the world, but if you don't have a really clear grasp of the design challenge you're trying to address, the user needs, the context, then the AI is just a tool without direction. It's unlikely to spit out truly meaningful or useful solutions.
Though the human insight is still paramount.
Totally. The lecture stressed that deep understanding of the design process itself, combined with what they called computational thinking, breaking down problems logically, is far more valuable than just being able to code a specific algorithm or use a particular piece of software.
That anecdote about the professor.
Yeah, the professor who deeply understood computational concepts and logic without actually writing code himself. It perfectly illustrates that the conceptual understanding is key.
That's actually really encouraging for designers, I think. You don't necessarily need to become a hardcore programmer overnight.
Not at all. You need to understand the principles and how to apply them strategically to design problems.
The lecture also mentioned top-down versus bottom-up approaches for using AI in design. Can you clarify those?
Sure. The top-down approach starts with a specific design problem or question you have.
Problem first.
Right. Problem first. Then you think, okay, what kind of data would help me solve this? And then what AI techniques could analyze that data to give me an answer?
Okay. And bottom up.
Bottom up is kind of the reverse. You start with the data you already have available.
Data first.
Data first. You look at it and think, okay, given this data and the AI tools we have, what interesting design questions could we answer? What problems might this data help us solve?
So one starts with the goal, the other with the resource.
Exactly. Both are perfectly valid strategies, and the best approach often depends on your specific situation, your goals, and the data you can access.
Right, being strategic about how we deploy AI. This seems to lead nicely into the idea of a data-driven design process, which the lecture outlined. How does AI weave into that workflow?
Yeah, the process described sounded quite familiar to design thinking, but with an AI layer. It starts, as usual, with formulating a hypothesis.
About the design.
Yeah, maybe about how users will react to a certain feature or the effectiveness of a specific visual element, something you want to test or understand.
Okay.
Then you collect relevant data, and here you think about top-down versus bottom-up, qualitative versus quantitative data types we discussed.
Right, gather the evidence.
Then comes a really critical step. Visualize and explore the data. Look for initial patterns, maybe use dimensionality reduction like TSNE to see clusters. Perhaps try out some very simple models just to get a feel for it. Don't just jump straight to complex AI.
Explore first.
Explore first. Then, based on that exploration, you select and train your main AI model. After training, you have to evaluate its performance, rigorously remember overfitting.
Using the validation set.
Exactly. And then comes the interpretation. What do the results actually mean in a design context? What insights can you draw?
And it doesn't stop there, right?
Definitely not. It's iterative. Those insights might lead you to refine your initial hypothesis, maybe collect different data, perhaps try a different AI model, or go back and tweak the design based on what you learned.
So the AI output isn't the end goal, it's fuel for the next design decision.
Precisely. Insight-driving design decisions. That's the core idea.
Now, to make all this complex model training happen, especially with deep learning, the lecture talked about GPUs and parallel computing. Why are these bits of hardware so essential under the hood?
GPUs, graphics processing units, yeah, they're pretty much essential for training large, modern AI models efficiently. And it all comes down to parallel computing.
Parallel computing.
Yeah.
Doing many things at once.
Exactly. Your typical computer processor, the CPU, is great at complex tasks done one after another sequentially. Very fast, but step by step.
Okay.
GPUs, originally designed for rendering graphics, which involves calculating colors for millions of pixels simultaneously, have a different architecture. They have thousands of simpler cores designed to do lots of relatively simple calculations all at the same time in parallel.
So, not one genius worker, but a massive team of apprentices.
That's a great analogy. The lecture used one like a single math professor versus thousands of elementary students for adding huge lists of numbers. For tons of simple additions, the student army wins on speed. Now, parallel computing has challenges, especially if tasks depend on each other. But it turns out that many of the core mathematical operations in training neural networks, specifically linear algebra operations on large matrices and tensors,
Matrices and tensors.
can be broken down into lots of independent calculations that are perfect for running in parallel on a GPU.
So the mass fits the hardware.
Exactly. This massively speeds up the training process. Training a complex deep learning model that might take weeks or months on a CPU could potentially be done in hours or days on a suitable GPU.
Wow, huge difference.
Yeah. The lecture used another good analogy. Painting an image pixel by sequential pixel versus having enough painters to paint every pixel at the exact same moment. That's the kind of speed up we're talking about. And it connects back to why GPUs were invented for graphics in the first place.
That makes the need for GPUs crystal clear.
Yeah.
Okay, as we start to wrap up this deep dive, the lecture touched on the future. AI in design, it might not unfold quite like we imagine it today.
That was an interesting point. The lecturer cautioned against assuming we know exactly where AI is heading, pointing to how wildly inaccurate predictions about the future were in the past. Think about predictions from, say, 1900 about the year 2000.
Right. Flying cars everywhere. Didn't quite happen like that.
Exactly. So the key takeaway is that technological progress, AI included, is often nonlinear and unpredictable.
So we shouldn't get too fixated on today's specific AI tools or trends as the definitive future of AI in design.
Probably not, no. The lecture even threw out the idea that AI might manifest in unexpected forms, maybe becoming much more integrated with physical robotics in ways we don't fully anticipate yet.
Interesting thought.
The core message seemed to be, tools come and go. The really important thing for designers is to grasp the underlying principles, develop that computational thinking, and remain adaptable. Learn how to learn and integrate new tools as they emerge.
That final analogy the lecture used about a rocket launch.
Oh yeah, the rocket launch being this incredibly complex outcome, but ultimately built on fundamental principles like basic arithmetic and physics.
Right.
It really underscores the idea that even the most sophisticated AI systems we see today, and the ones to come, are ultimately grounded in relatively simple foundational concepts: logic, statistics, optimization.
Like the dots and lines.
Like the dots and lines. Understanding those building blocks gives you the power to understand, critique, and creatively leverage even the most complex AI tools now and in the future. It requires creativity and understanding, not just technical skill.
So to try and bring this all together for you, the listener, listening in.
Yeah, the real core idea we've dug into today is that machine learning, which powers so much of AI, is fundamentally about finding patterns in data. We use that dots and lines analogy to visualize it.
And we saw how crucial it is to understand your data, prepare it properly through preprocessing.
Right, and knowing the different types of problems AI can tackle, like regression for prediction, classification for categorization.
And maybe most importantly, the need to clearly define the design challenge you're trying to solve before you even think about the specific AI technique.
Absolutely. That domain knowledge, that design understanding is key.
And hopefully, we've managed to show that while AI can seem like this intimidating black box, the underlying principles are actually quite accessible.
And very relevant to how designers already think, analyzing information, iterating, looking for patterns, solving problems.
So maybe take a moment after this to think about the data you already encounter in your own design process. What patterns might be hiding there? What problems could you perhaps approach in a new way with these concepts?
Which leads us to maybe a final thought for you to chew on. How might really internalizing these foundational AI concepts actually reshape your own design thinking? How could it unlock innovative possibilities, maybe solutions you haven't even considered yet?
It's a fascinating space, constantly evolving. We really encourage you to keep exploring. Thanks for diving deep with us today.